The purpose of today's lab simulation is to verify the index of refraction of water. To access this lab sim, you're going to go to Google Classroom, click on the written instruction page. At the top of the written instruction page, there's going to be a link. That link will take you to a page that looks like this. On that page, you're going to see a laser, or at least a pretend laser, with an on switch right here. In the bottom left-hand corner, you're going to see a protractor. You're going to use that throughout this lab to measure the angle of incidence and angle of refraction in each trial. Now, on the right side of the page, you're also going to see the index of refraction of air and the index of refraction of water. Now, remember what the problem in this lab was. It wasn't to find the index of refraction of water. It was to verify the index of refraction of water. We know the value of the index of refraction of water is 1.33. What we want to do is perform an experiment to get a value that is as close as possible to 1.33. The first thing you should do before you actually start collecting any data is to move the protractor in place. So click on the protractor in the bottom left-hand corner, drag it over to the boundary between the air and the water. Make sure that 0 degrees is lined up perfectly with the normal line, and 90 degrees is lined up perfectly with the boundary. Turn on your laser, and when you do, you should see a beam of light that strikes the boundary. Most of that beam of light is going to refract. That's this beam right here. You're going to see a little bit that reflects right here, but you're not going to pay any attention to that. You're going to measure the angle of incidence, as always, from the normal line. So it's this angle right here. Use your protractor to determine what that value is. The angle of refraction is also going to be measured from the normal line. Determine the value of that with the protractor as well, right here. Record those two values right here and here. Make sure you record the value of the index of refraction of air as well, which is 1.00, and the index of refraction of water, which is 1.33. Now, this is the known value, or the theoretical value, of the index of refraction of water. One of the last things you're going to do in this lab is do a percent difference calculation for the value for the index of refraction of water that you get. You're going to compare the value that you get to this theoretical value by doing a percent difference calculation. I'll explain that when we get a little bit further along. Do another trial. Notice this time the angle of incidence is quite a bit different than it was in my first trial. The angle of refraction is quite a bit different as well. This is my refracted ray. We're not going to pay any attention to that in this trial or any other trial. Make sure that you do at least 10 different trials, 10 different angles of incidence, and 10 different angles of refraction. Once you have all of those values of the angle of incidence and angle of refraction, then you're going to create a new table. The new table is analysis, and that analysis table is going to have two columns, sine theta 1 and sine theta 2. So if theta 1 was 30 degrees, then sine theta 1 would be 0.5. If theta 2 was 45 degrees, then sine theta 2 would be 0.707. Fill in this entire table with all the values of sine theta 1 and sine theta 2. And then, you guessed it, you're going to plot a graph. Your graph is going to be sine theta 2, versus sine theta 1. Don't forget your title. You know how to put a title in. All your data points should be relatively close to a straight line. Make sure you plot a trend line, which should be a linear trend line, and display the equation on Google Sheets. Then, you're going to do something that we've done a couple of times earlier this year. We've done it more if we were still in class. You're going to determine what the slope of this graph represents, and that's going to, in turn, get you the index of refraction of this glass. So, we know the equation for any straight line graph from math class, maybe grade 9, is y is equal to mx plus b. That's this graph or any other straight line graph. The y-axis is sine theta 2. m is the slope of the graph. Now, we don't want to get that mixed up with mass, so we're just going to write in the word slope. The x-axis of this graph is sine theta 1. B stands for the y-intercept, and you should find in this lab that your y-intercept is either 0 or a value that's really, really close to 0. In the end, you can get rid of that because it's either 0 or so close to 0. Now, what we want to do is come up with an equation from our data sheet that has the same variables, sine theta 2 and sine theta 1 in it. That's going to be our Snell's law equation, sine theta 1 over sine theta 2. Remember from a couple of weeks ago that this equation has 4 parts to it: sine theta 1 over sine theta 2, v1 over v2, lambda 1 over lambda 2, or n2 over n1. Because we're trying to verify an index of refraction, we want to use the n2 over n1 part of the equation. Now, rearrange that to solve for sine theta 2, because that's what we solved for in the first equation. So I'm going to take the sine theta 2 up by multiplying, the n1 up by multiplying, and the n2 down by dividing. So I end up getting sine theta 2 is equal to n1 over n2 times sine theta 1. Now what we're going to do is cross off variables that appear in both of those equations. Sine theta 2 appears in both. Sine theta 1 appears in both. That leaves us with slope in the equation from the graph and n1 over n2 in the equation from our data sheet. That means in this particular straight line graph that the slope of the graph is equal to n1 over n2. Google Sheets gave you the slope of the graph. N1 is air. You're going to use the known value of 1.00 for that, and then you're going to calculate N2, the index of refraction of water. Now, you already know what that is, right? You already know that that's 1.33. You're going to compare your experimental value to the theoretical value that you recorded when you were recording your data. Now, how do you do that percent difference calculation to determine how close your experimental value is to your theoretical value? Your percent difference calculation is going to be found by taking the experimental value, which is what you just got, minus your theoretical value that you recorded earlier on in the lab, over your theoretical value. I'm going to put these two vertical lines beside it. That just means absolute value. So in other words, whatever we get here, positive or negative, it's going to become a positive value. We're going to multiply it by 100. Now, because this is a lab sim with cooked up data, the percent difference should be low. If it's below 10%, that's the number we'll use there. If it's below about 10%, we'll say that we did, in fact, verify the index of refraction of water. If it's above 10%, then you're going to say you didn't verify the index of refraction of water. Now that you have that percent difference calculation done, you're going to write out a conclusion. Your conclusion has two parts to it. What is the index of refraction that you found for water? And how do you know? In other words, you're going to just briefly explain the analysis that you did up here to determine what that index of refraction of water is. That's it. Because this isn't an actual lab, you're not going to do any sources of error. You've done your conclusion, you've done the lab, submit it, and then you're done for the week.